critical value method when you have two independent samples. So with these three problems here, we're going to assume all the preconditions have been met. And this is basically a how-to video. And hopefully we'll have enough variety on the population parameter and whether or not we use z-scores or t-scores for this to be of help to you. So we have three examples there, and let's just start with the first one. So I'm going to scroll down here because I've already got the first one set up. Okay, a certain state has a law that all motor vehicles must have both a front and a rear license plate. Among 2,049 passenger cars, 239 had only rear license plate. So our population parameter here is a proportion. Let me do this in black. And of course, we have two proportions. So our first population, our first sample is on passenger cars. And so the sample size is that. And my number of successes. So successes are what you're testing for, and we're looking for cars that only have rear license plates. So it's kind of a logical, doesn't make much sense that way. A success is if a car is breaking the law, but nevertheless, we're testing for the number of cars that only had rear license plates. And then with the commercial trucks, which is our second population, the sample size was 334, and the number of successes, i.e. the number that only had rear license plates, was 45. Test the hypothesis, or test the claim, that the passenger car owners violate the license plate laws at a lower rate than the owners of commercial trucks. So the claim in symbolic form is that the first population, the first proportion of passenger cars that violate the license plate laws, so the proportion of cars that violate the license plate laws is lower, less than. So that's my initial claim in symbolic form. The null hypothesis is always equality. And then when I get to the alternative hypothesis, I look at the symbol in the initial claim, and if it's allowed, I keep it. And of course, for the alternative hypothesis, you can only have strictly less than, strictly greater than, or not equal to. So the strictly less than symbol is allowed, so I keep it for the alternative hypothesis. Now that I have the alternative hypothesis written out, the symbol in the alternative hypothesis determines the type of test, and we're going to have a left-tail test. Now, since the population is a proportion, then my critical value and my test statistic are going to be z-scores, or z-values. And since I have a left-tail test, then all of the rejection region, or the critical region, is in the left tail. Now, alpha is the total area in the rejection region. So when I have a left tail test, that area is going to be alpha. Now, what is alpha? Well, if ever you see the word significance level, that is alpha. We do not have the word significance level. We have not been told what alpha is. When you are not told alpha, the default, what you use for alpha, is 0.05 if you're not told alpha, which we are not in this problem. So this left area is 0.05. So I'm going to have one critical value. It's going to be a negative z-score. And then to get this z-score, I need to use the command normal CDF. And that's what you use if you're trying to find the z-score and you have that left area. So I'm going to do that now. I'm going to take everything to 3 decimal places. So to get to normal CDF, I do second bars. And I come down here to normal CDF. And my left area, oh, sorry, I don't do normal CDF. Need inverse norm. I got my norms mixed up. So sorry about that. And I need to give left area. So second, get out of here, second mode. All right, let's try it again. Second bars. And let's go to inverse norm. That's what I need for this. Okay, my left area. So I'm going to press enter. My left area, and notice that the default here is left, is 0.05, the shaded region, the rejection region. And I'm in a standard normal distribution. And then we click enter. So if I take that to 3 places, I'm going to have minus 1.645. That's my critical value. Okay, now I need to get the test statistic, because with the critical value method, I need to see if the test statistic is inside the rejection zone. So now I'm going to go to tests. So I'm going to click stat, go over to tests, and I'm going to come down here to prop proportion. So I have 2 samples, z-test, and press enter. Okay, so the number of successes in my first population is 239. And my sample size with the cars is 2049. My number of only rear license plate with the trucks is 45. And my sample size with the trucks is 334. Then on the next line, I need to give it the symbol that was used in the alternative hypothesis. And we see here that the symbol used was the less than symbol. So I need to scroll over to the less than symbol and then click enter. And then I come down here to calculate. And this is how I'm going to get the test statistic. Yes, there is a formula you can use, but it's horrible. And why use a horrible formula when you're allowed, well, the university I teach at expects you to be able to do this with calculators. This is your test statistic. So the test statistic, and I'll take that to 3 places. It's also a z-score, and it's minus 0.946. Now, where is that test statistic on this horizontal line? Well, it's to the left of 0, and it's to the right of minus 1.645. If you think of it as a number line, it'd be about here. So the main thing that we get from this is the test statistic is not inside the rejection zone. If it's not inside the rejection zone, then we do not reject the null hypothesis. So we're assuming the null hypothesis is true. We do not reject the null hypothesis. Now, the fancy schmancy way to say that is fail to reject. So, i.e., fail to reject the null hypothesis. Now I have to formulate a wording of the final conclusion. The only 2 things I need to know about the final conclusion is what the original claim was and whether I reject or fail to reject the null hypothesis. So I'm going to get rid of everything else now. And just write that. because now I'm going to come down here and we'll get the wording of our final conclusion. So we start here. Did the original claim contain the condition of equality? No, it did not. The original claim had the strictly less than symbol. Did not have any equality in it. Did you reject the null hypothesis? No, we did not. We failed to reject it. And so I can start typing. There is not sufficient evidence to support the claim that. And then what we're going to do now is go back and get the wording of the claim. So we're not going to say there's not sufficient evidence to support the claim that P1 is less than P2. Our final wording is going to be all English. There is not sufficient evidence to support the claim that the passenger car owners violate license plate laws at a lower rate than owners of commercial trucks. All of that. So is one of those wishy-washy results. You'll get two results that are conclusive, either supporting or rejecting it, and then you'll get two results that are kind of wishy-washy. And this is a there's not enough evidence to support it. So we're neither rejecting or supporting it. We're just going to say there's not enough evidence to support it. Okay. All right, so that's the first one down. So let's look at the second one. And I'm going to copy that and come down here. Get rid of this one. Okay. University professors are rated on a scale from 1 to 5 by students at the end of the semester. A sample of 40 students who submitted course evaluations for female professors. Okay, so my first group is female professors. So in the sample size is 40, had a mean of 3.79. So my population parameter here is mean. Okay. And a standard deviation. Now, that's the sample standard deviation. So that's not sigma, that's S. While a sample of 53 students who submitted course evaluations for male professors, okay, so that sample size is 53. The sample had a mean of 4.01, and the sample had a standard deviation of 0.53. And use a 0.01 significance level, so alpha is 0.01, to test the claim. So the claim in symbolic form is that female and male professors are rated the same. Okay, so the mean scores for all female professors is going to be rated the same as male professors. Okay. So yes, in the two samples here, they're not the same. Okay, the mean score is not the same, but is that enough of a difference to be significant is what we need to be asking ourselves. Okay, now nowhere here do they tell us what the population standard deviations are. And nowhere here have they told us that even though these are unknown, that we could assume that they were equal. So it's not known if they are equal. So sometimes they can be unknown, but you'll told that they come from a population where they're equal. Okay, that's going to make a difference also in what test we use. Okay, so I've got the initial claim in symbolic form. My null hypothesis is always equality, always. My alternative hypothesis, I'll write it with a 1 this time. Some books use an A, other books use 1. I look at the initial claim. The equal sign is not allowed. You're only allowed to have strictly less than, strictly greater than, or the not equal symbol. So if the symbol is not allowed, you take its complement, and the complement of equal is not equal. Now, in the alternative hypothesis, the symbol is not equal, and that means I'm going to have a two-tailed test. Okay, so I might draw it over here. I'm going to have 2 rejection regions. I'm going to have 2 critical values. Now, since the sigmas are unknown, my critical values are going to be t-scores. My test statistic is going to be a t-score. So the critical values and the test statistics are going to be t-scores. Also, alpha is the total rejection region or critical region. It's the total rejection area. I have 2 rejection areas here, so each of these areas are alpha over 2. And 0.01 divided by 2 is 0.005. So each of these areas is 0.005. Now, if I get the negative critical value, then by symmetry I can get the positive one just by taking the absolute value. Now, since we have t-scores, I'm going to have to use the command inverse t, not inverse norm. That's what you use for z-scores. And I must tell it the left area, and then I have to get degrees of freedom. Now, when you have 2 samples, then the degrees of freedom is going to be the smaller sample size minus 1. So my left area here is going to be 0.005, and my degrees of freedom, well, my smaller sample size is 40, and 40 minus 1 is 39. Okay, so that's what I'm going to put into my calculator to get this left critical value. So let me get out of here, then get into second vars, and come down here to inverse t. And I must give left area. So for this negative critical value, I've got the left area, 0.005. And the degrees of freedom are 39. Okay, and if I take that to 3 places, that's going to be minus 2.708. And then by symmetry, my positive critical value is going to be positive 2.708. So those are my 2 critical values. Now I need to see what the test statistic is, and is it going to be inside one of these critical values? Okay, so I'm going to get my calculator to tell me what the test statistic is because the formula is horrible. I'm going to go over to tests. Now, I have 2 samples, and everything's a t-score. So I'm going to come down here to t-test is what I'm going to have. No, I'm going to have 2 samples, sorry. I have 2 samples, and I'm going to use the t-test on them because everything's a t-score. Now it wants to know, were you given the raw data or were you given summary statistics? And we were given summary statistics here. So I'm going to scroll over to where that's stats and I'm going to press enter. Okay, so for my first sample, the mean was 3.79. And for my first sample, the standard deviation was 0.51. And for my first sample, you can see I've got old data in there. I'm just going to overwrite it. With my first sample, the female professors, the sample size was 40. Okay. And with my second sample, the male professors had a mean of 4.01. And the sample standard deviation for the male professors was 0.53. And then the sample size for the male professors was 53. Now, what we need on this line is the symbol in the alternative hypothesis. And so my latest problem has been saved there, but this is my alternative hypothesis and the symbol is the not equal symbol. So that's what I need to highlight. And it's over it at the moment. I'm going to press enter. Now we come to having to make a decision on this pooled. And this is why if you're told that even though sigma 1 and sigma 2 are unknown, if you're told that they come from a population where they're the same, then you will pool. If you don't know whether or not sigma 1 and sigma 2 are the same, then you do not pool. So we are choosing no. So even though sigma 1 and sigma 2 are unknown, there's that extra bit of information like, are they the same even though they're unknown, or do we not know anything about that? And we haven't been told that they're the same. So we are not going to pool. Okay. So now I should be ready to go, should be good to go. And I want the test statistic. And this number up here is my test statistic. So I'm going to make some space here. I'll write it in red. And I'll take it to 3 places. The test statistic is minus 2.025. Okay, so this test statistic, that's where 0 is going to be. And minus 0.25, if this is a number line, it's going to be about right there. But the key thing is that it's not inside the rejection zone. So the test statistic is not inside the rejection region. So we do not reject the null hypothesis, i.e. we fail to reject. Now, if I'm going to come to the wording of the final conclusion, the only thing I need to know for that flow chart is the original claim and whether or not we rejected or failed to reject the null hypothesis. Okay, so I'm going to get rid of all of this and I'm just going to put up the original claim, the claim that the female and male professors are rated the same, and then we concluded that we will fail to reject the null hypothesis. So we do not reject the null hypothesis. Okay. So now let's come down here. So, did the original claim contain the condition of equality? It certainly did. Did you reject the null hypothesis? No, we failed to reject it. And so that brings us to this result. And I'm going to start typing. There is not sufficient evidence to warrant rejection of the claim that female and male professors are rated the same. Okay. All right. Okay. So let's look at the third one. Radiation in baby teeth. Let me copy this one down here. And let's get the list. Okay. Listed below are the amounts of strontium-90 in simple random sample of baby teeth obtained from Pennsylvania residents and New York residents born after 1975. So we're going to have two groups. Our first group is Pennsylvania, and our second group is going to be New York. Okay. Use a 0.05 significance level to test the claim, okay, that the mean amount, okay, so once again, our population parameter is a mean. The mean amount of strontium-90 from Pennsylvania residents is greater than the mean amount of strontium-90 from New York residents. Okay. So my null hypothesis is always equality. The alternative hypothesis, well, I look at the claim, the greater than symbol is allowed, so I keep it. And so the symbol there tells us we're going to have a right tail test. Okay, so all of the rejection region is going to be in the right tail. And so this area is going to be, alpha is the total area in the rejection region. There's only one rejection region. And we've been told that alpha is 0.05. Okay, so I have not been given summary statistics. I've been given the raw data. So I do not know the population standard deviation. And we have not been told anything about them being the same. So we will not pool. So do not pool. Okay. So there was going to be one critical value. It's going to be a t-score because the sigmas are unknown. It's going to be a positive number. So again, I'm going to use the inverse t command, but just remember, for inverse t, you must give it left area and then degrees of freedom. Okay, now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Both of these samples have 12 data entries, so the degrees of freedom is going to be 11. And the left area, well, the right area is 0.05. The total area under the curve is 1. And I don't even have to calculate that. I can just put it in my calculator like that. It'll do the work for me. So let me get out of here and get into second vars, and then come down here to inverse t. I must give it the left area. Now, it has my old data from a previous problem. The left area is 1 minus 0.05. If you give it 0.05, you've told it the right area, and it will take that as left area, and you'll get a negative critical value. You must give it the left area, and the degrees of freedom in this case are 11. Okay. And so, as expected, my critical value is 1.796. Now let's get the test statistic. If I go to the test statistic, press stat and go to tests, I do have a 2 sample, and I want to do a t-test because critical values and z-scores, test statistic are z-scores. I have not been given summary statistics. I've been given the raw data. Now, the default is you take your first population and save it in list 1, and you take your second population and save it in list 2. So that's what I'm going to do. So I'm going to get out of here. I'm going to press stat and then enter. Okay, so if you have any occupied lists, you're going to have to delete them, but I don't. So I'll put Pennsylvania in list 1. So this takes the most amount of time. And I'm using an emulator, which is a pain in the butt. 149, 130. I should have done this beforehand, but never mind. In fact, I think I'll put it on hold, and I'll do this while I pause the video. Okay, so I have now put my 2 lists in. First list is Pennsylvania. Second list is New York, and I've double checked them. So now I'm going to press stat. And I'm going to scroll over to calc. Actually, no, I should have gotten out of that window. Now I'm going to press stat. I'm going to scroll over to calc. Then tests, and I want 2 sample t-test because my critical value and my test statistic are t-scores. And I have the raw data, and list 1 is my Pennsylvania data. List 2 is my New York data, and the default, you have 1s there for frequencies. Okay, on this line, they want to know what was the symbol used in the alternative hypothesis, and the symbol used in the alternative hypothesis was the greater than symbol. So you want to scroll over to that and highlight that. Press enter. And we are not pooling because we have not been told to assume that the sigmas are equal. Okay, that's all looking good. So I'm going to click on calculate. This is my test statistic. Notice it's a t-score. So I'm going to write it in red. And I'll take it to 3 places. It's so it's a t-score, 3.265. And then on this horizontal, if you think of that as a number line, where would 3.265 be? And it would be to the right of 1.796. So it would be over here somewhere. And we can see that the test statistic is inside the rejection zone. And so we reject the null hypothesis. Now, to get my wording of the final conclusion, the only thing that I need is the original claim and then whether or not I rejected the null hypothesis. So I'm going to get rid of everything else, and the original claim was that, and we rejected the null hypothesis. Okay, so now I'm going to scroll down here to the wording of the final conclusion. Did the original claim contained the condition of equality? No, it did not, because the symbol was strictly greater than. Did you reject the null hypothesis? We certainly did. And so now this is what we use. I'm going to start typing up here. There is sufficient evidence to support the claim that, so we get a definitive answer on this one. That the mean amount of strontium 90 get rid of that. From Pennsylvania residents is greater than the mean amount from New York residents. Okay. So I hope there have been enough examples. There were 3 examples, enough to give you kind of an idea of how it goes with critical values or with hypothesis testing. You've got to know whether or not your critical values and test statistics are z-scores or t-scores, because that makes all the difference on what kind of test you use. And so you can really go down, the dominoes tend to fall pretty badly if you get that wrong from the get-go. Okay, so many steps to hypothesis testing. Lots of things can go wrong. So I just hope the video's helped you. If it has, I'd appreciate it if you could give it a like and also subscribe to my page. Okay, hope to see everyone again. Thank you.